Hello and welcome back to Chapter 2. Today we're going to look at 2.2, which deals with polynomial functions of a higher degree. Now in this section we're going to look at the graphs of polynomial functions, and there's two things that I want you to remember. One, polynomial functions are continuous, okay, and remember that continuous means that there's no breaks, holes, gaps, anything like that. You should be able to take your pencil, trace the function, and never pick it up. And then the second thing I want you to know is that graphs of polynomial functions have only smooth, rounded turns. You will never see a super sharp term, kind of like an absolute value function that has like almost a V shape. That is not a polynomial function. A polynomial function will always have smooth curves on their turns. So if we look at this graph, graph A has smooth turns, it's continuous. While on the other hand, graph B, it does have smooth turns, but if I follow the function, I all of a sudden hit this point here, then I have to pick my pencil up, drop it down here, and then continue on. So it is not continuous, therefore this is not a polynomial function. Okay, and when we look at this graph here, again, we have nice smooth turns. This one has a couple more than the previous one. It's continuous. This graph here, although it is continuous, it does have a sharp turn before we go ahead and head in the positive direction, and a polynomial function will not have a sharp turn, therefore the function of an absolute value is not a polynomial function. Now when we look at polynomial functions, the most basic type of a polynomial function is what we call a monomial. And if you remember, monomial means that we have one term. Kind of like in this notation right here. If we have more than one term, it's called a polynomial because poly means more than one or many. And if it's a binomial, that means two, trinomial, three, and so on. So this right here is our most basic form of a polynomial function. And if we have a polynomial function in this format, this is what we call a power function because x to the n is a power. Now with power functions, we have two different types of power functions. We have even functions and odd functions. And the even function and odd function stuff comes from the actual exponent itself. So if I have something like x to the fourth, x squared, x to the sixth, x to the 10th, these exponents are all even numbers, therefore they are even powers, or even power functions. If you graph all of these functions here, you will see that the graphs have similar characteristics, and we're going to go over that here in just a minute. Likewise, if we have an odd function, this is going to be something like x to the first, x to the third, x to the seventh, x to the 13th, etc. I'm going to look at my exponents. These are all odd numbers, therefore giving us odd power functions. And these graphs here will all have the same type of characteristics as well. So for example 1, it says to sketch the graph of the function f of x equals the quantity of x plus 5 to the fourth power. Because x plus 5 to the fourth power is really an even function, I know that this is going to look something similar to that of a parabola, because a parabola is also an even function. So when I go to graph this, I'm going to start out with my x-intercept, or in this case, because it's an even function, I don't have an x-intercept, but my vertex is actually going to hit on the x-axis, and that's going to hit at x equals a -5, so right here. And if I graph it, I will see that I end up with something that looks like this and this. Oops. Like that. And you can graph this on your calculator to get a little bit better picture. The next thing we're going to look at when graphing polynomial functions is what we call the leading coefficient test. What this does is it's going to tell us that as we move without bound in either the left or the right direction, a graph of a polynomial function is either going to eventually rise or fall. And there's two things that we have to look at. First, we have to look to see if it's an even function or an odd function. So if it is an odd function, we're going to look at our leading coefficient, and if it is positive, then that's going to tell us that our graph is going to fall to the left, rise to the right. So if you look at something like x cubed, this is an odd function. The coefficient on x cubed is positive, therefore I'm going to end up with something that looks like this. Now if you look at this graph, my graph is going to fall to the left and it's going to rise to the right. Now if my leading coefficient is negative, it's actually going to be opposite of that. So if I have something like negative x cubed, then we're going to end up with something that rises to the left and falls to the right. So something that looks more like that. And if you can't remember which rule goes with what, if it rises or falls, graph it or sketch it. You don't have to memorize all of these different rules. The next thing we're going to do is look at an even function. With an even function, it says that if our leading coefficient is positive, then our graph is going to rise to both the left and the right. So think of the classic case of x squared. X squared is a parabola, and it rises on both the left and the right sides. Now if we look at the opposite of that, where our leading coefficient is negative, or a case like a negative x squared, hopefully by now you realize that that function is going to be like an upside down parabola, and that both our left and the right sides are going to fall. So let's go ahead and take a look at an example that deals with this type of a test. Example 2 says to describe the right hand and left hand behavior of the graph of each function. So when I look at part A, which says f of x equals 1/4 x cubed minus 2x, the first thing you should take note of is the fact that I have an odd function and a positive coefficient. So because I have an odd function and a positive coefficient, you should instantly think that as we're going to the left, your graph is going to fall. As you go to the right, your graph is going to raise. So we're going to write that down, and we're going to say something to the effect that we're going to fall to the left and rise to the right. Okay, now if we look at part B, you hopefully will look at this and realize you have a negative coefficient, and again we have another odd function. It's the leading coefficient of the highest degree. Like in this case, I don't care about the x squared, I don't care about the 1, I only want to know what that first term is doing, or the term that's attached to the highest power. So because I have a negative odd function, I know that my graph is going to rise to the left and fall to the right. So we're going to rise to the left and fall to the right. And let's fix that in there. Another critical thing that we want to look at when we're dealing with polynomial functions and graphing are the zeros of the function. Now, at most, your function has n real zeros. So if I have a third degree polynomial, at most that I can have are 3 real zeros. I can also predict the number of turning points I have based upon the number or the degree of my polynomial. So if I have an n degree polynomial, at most I can have n minus 1 turning points. Now turning points are really your maximum or minimum points. So if I have something like f of x equals, let's just say x to the 5th plus 1, I know that I'm going to have at most 5 real zeros. It doesn't mean I have to have 5 zeros, but I will never have any more than 5 zeros. And then at most, I'm going to have n minus 1, which would be 4 minimum and maximums. Again, I don't have to have 4, but this is just the maximum amount that I can have. Now, if we have real zeros of polynomial functions, then all 4 of these statements here are equivalent. Okay, we can say that at x equals a, this is a zero of our function. We can also say x equals a is a solution of the polynomial, because remember, a 0 is the same thing as a solution, which is the same thing as an x-intercept, which is the same thing as a root of a function. We can also take the fact that when x equals a, if I want to set this whole thing here equal to 0, I have to subtract my a value to get 0. Now I have a factor. So that's really what 3 is saying. It says x minus a is a factor of your function, and the coordinate point a0 is an x-intercept of your graph. So in example 3, it says find all the real zeros of x cubed minus 12x squared plus 36x, and then we want to determine the number of turning points. Well, what we're going to have to do is we're going to take that x cubed minus 12x squared plus 36x, and we're going to set it equal to 0. Then we're going to have to factor. So I can factor an x out of everything, and we have x squared minus 12x plus 36 equals 0. And if I continue to factor this, I have x times x minus 6 times x minus 6 equals 0. And you really can write that as x times a quantity of x minus 6 squared equals 0. So now if I take each factor, set it equal to 0, I end up with x equals 0 and x equals 6. So these are my two x-intercepts, or my two solutions. Now to find the number of turning points, I'm going to look at my largest exponent, which is 3. I'm going to subtract 1, and I get 2. So at most, on this graph, I can have 2 turning points, and I have at most 3 zeros, but I just calculated my real zeros to be 0 and 6. Now, on the previous example, we did have a case of a repeated 0, and a repeated 0 is something like that x minus 6 squared. We say it's a repeated 0 because I really have two solutions. This is x minus 6 times another x minus 6, and if I got x by itself, both of them will give me a value of 6. So we can say that a factor, x minus a raised to the power of k, where k has to be something greater than 1, has a repeated 0 at x equals a, and this is a multiplicity of k. So in this case, this is x equals 6 was our 0, and our multiplicity was 2. Now if k is odd, then our graph will actually cross the x-axis at x equals a. If k is even, okay, as in the case that we had in the previous example, then our graph will just touch the x-axis. It will not actually cross it. Now, one thing I want you to remember or make note of is that a polynomial function can only change signs at the zeros. So when we're looking between two zeros, a function is either going to be entirely positive or entirely negative. Now, if the zeros are put in order, okay, so you can calculate all of your zeros, and then if you put them in order from like smallest or most negative to the most positive, then this does what we call divide our number line into intervals or test intervals. And we're going to look at test intervals here in the next example. So example 4 tells us to sketch the graph of f of x equals 3x to the 4th minus 4x cubed. And the one thing I want you to make note of, this might seem kind of confusing at first, but this is assuming that you do not have your awesome little TI-84, TI-83 graphing calculator. This is how you do all of this stuff without a calculator. So I do expect to see the work on these problems, and you can use your calculator to verify, but you have to show me the work on these. So for example 4, the first thing we're going to do is we're going to use our leading coefficient test. Now our leading coefficient test says that my leading coefficient, which is this 3 here, is positive, and I have an even function. So because I have a positive even function, and let's just write this down. We have a leading coefficient test. So a sub n is greater than 0, and we're even. So what that tells me then is I can predict the ends of my graph to both be facing upward, like this. And then whatever happens in the middle, that's kind of up in the air right now. Then, my next step is going to be to find the zeros. So to find the zeros, it looks like I can factor out an x cubed. So then I'm left with 3x minus 4, which tells me that I have an x at, a 0 at x equals 0 and at 4/3. So now I'm going to create my test intervals and plot a few points. So my test intervals are going to be everything from, because I do have these in order already, from a negative infinity to 0. Then I have to look at the interval from 0 to 4/3. And then I'm going to look at the interval from 4/3 to a positive infinity. Now the next thing I have to do is I have to create a representative value. And you can just pick anything, it doesn't matter. Personally, I like to pick stuff that works out kind of nice. So for my representative value between a negative infinity and 0, I'm just going to pick a -1. Something between 0 and 4/3 would be 1, and something between 4/3 and infinity, 1.5. Again, it does not matter, just make it numbers that work out kind of nice. Then what I'm going to do is I'm going to take this number here, plug it into my function to find my f of x value. So when I do that, when I plug a -1 in, I get 7. When I plug a 1 in, I get a -1. And when I plug in 1.5, I got 1.69-ish. So then I'm going to go to the sign and say my sign is positive here, negative, and positive. And then for my point, I end up being able to graph the point -1, 7, 1, -1, and 1.5, 1.69. Now one thing I'm going to make a note of before I go ahead and graph this is I'm changing from positive to negative to positive. So that tells me that somewhere between my point -1.7 and 1.5, 1.69, I'm going to actually dip below the x-axis because my function value changed signs. So now if I go and plot these points, we're going to end up with something that looks like, now before I go ahead and connect the dots, this point here, and this point here are all of my coordinate points that I've calculated over here. This point here, 0, 0, and 4/3, 0, these are my zeros that I calculated on the previous slide. So before I go in and, now I'm going to go ahead and connect those, and you'll see that you end up with something that looks like this. Now, both of our ends, as we predicted, we're both going to be rising on the left and the right. We have our zeros. We did predict that we would have a negative y values in between the point 0 and 4/3 because of the sign change up here. So it kind of looks like we've got all of the pieces of our graph now. The last thing we're going to look at is what we call the intermediate value theorem, which is going to be IVT from this point forward. And what this does is it kind of helps us locate our real zeros. And essentially what it says is if you have two numbers that they're going to call it A and B, and let's just say A is less than B, if you have a function, and it's a polynomial function, and f of A is not equal, I'm sorry, that should read f of A, not x. So f of A is not equal to f of B, then on the interval from A to B, you have a polynomial function is going to take on every value in between f of A and f of B because a polynomial function is continuous. So in order to see how this helps locate our real zeros, it's going to kind of fall back to that sign change thing. If you evaluate your function at value or at random values and you go from positive numbers to negative numbers or negative numbers to positive numbers, you know that you've crossed the x-axis. So example 5 says to use the intermediate value theorem to approximate the real zeros of f of x equals a negative x to the 5th plus 3x cubed minus 2x plus 2 to the nearest hundredth. Now, what I've done is I've just gone in and I've picked some random points. And I'm going to pick something like negative 1, 0, 1, and 2, just for a starting point. Now if I plug in negative 1 in, I get 2. If I plug 0 in, I get 2. If I plug 1 in, I get 2. And if I plug in 2, I now get a negative 10. So what this has done now is this has told me, because all of these values here were positive, these are all up above my x-axis. Now all of a sudden at x equals 2, I jump below my x-axis, so that tells me that I have a 0 in between the points 1 and 2, and I'm going to have to fine-tune them. So then what I would do is I would create another table that would go between, in my x values, and I would go from, like, maybe go by tenths, go 1, 1.1, 1.2, 1.3, and continue to evaluate until I found out what my actual 0 was. And if you go ahead and solve this, you'll see that your 0 is between 1.64 and 1.65. Now, I will go over questions on this in class tomorrow, but please try a couple problems just to see if you can do some of this on your own. And now it's time for our fun fact. And today's fun fact says, or joke, why can't you trust atoms? For those of you in chemistry, you should know this. That's because they make up everything. On that note, have a good night, and we'll see you guys tomorrow.